Hello everyone, my name is Babarensa Olaiwola. I'm here to make mathematics understandable as possible. Today's video is on limit of a function. Limit of a function. The limit of a function at a point in its domain, only if it exists, is the value that the function approaches as its argument approaches the point. The limit of a function is used to analyze the behavior of functions near a particular input. It has applications in analysis and modern calculus. The limit of a function got the modern idea when Bernard Bolzano, an Italian mathematician, introduced the epsilon delta technique in defining continuous functions. In 1821, a French mathematician, Augustin Cauchy, discussed limits and defined continuity of y equals f of x. Now, it was a German mathematician, Carl Theodor Weierstrass, that introduced the limit notation and gave the modern epsilon delta definition of limit. Placing the arrow below the limit symbol was introduced by an English mathematician, Harold Hardy. A function f of x has a limit L as x approaches x0. Let's consider this example that you want to get a coffee from a coffee shop. You had a function and the coffee shop is the limit of the function. Then you take steps to get to the coffee shop. Let's say the first step is x1, which is closer to the coffee shop. Now the next step, let's call it the x2, which is much closer to the coffee shop than the x1. Then let's say x3, which is closer to the coffee shop than the x2, and it continues like that. Eventually, you get to the coffee shop and you order for the coffee, and you are given the coffee. Once you are given the coffee, definitely you will be excited. This coffee is the limit itself. Now let's reconsider this in another form. You are still the function and you want to go to the coffee shop. You take the same step, x1, x2, x3, up to the point you get to the coffee shop. But when you got there, you then discover that the coffee shop does not exist. Definitely, you are going to get angry. At this point, it means that the coffee shop has been moved to another town. That means it does not exist. We use the infinity. What happens to f of x equals x squared minus 1 as x approaches 2? To do this, we can do it graphically. The vertical line represents the f of x. The horizontal line represents the x itself. Then when we plot the graph, it's going to look like this. Now, let's place 2. And we want to approach this. Let's draw a line. And to the f of x, we don't know what we're going to get. Now, we can start to put some values that are relatively close to 2, such as 1.9, 1.99, 1.999. As we put this value into the f of x, we are going to get 2.61, 2.9601, 2.996001. In this case, we know that we can take the limit as x tends to 2 of x squared minus 1. And if we look at this function, by the time we input the values of x, we can see that the values we have is relatively close to 3. Now, if we take this function now, we are going to get 3. Mathematically, f of x equals the limit as x tends to x0 for every epsilon greater than 0. There exists data greater than 0 such that 0 is less than the absolute value of x minus x0 less than delta, which implies that the absolute value of f of x minus L is less than epsilon for x0 and L are real number. This is a delta epsilon delta definition of limit. Now we give some theorems of limit. If we have limit x tends to a, then we get a, we call it the tautological rule. When we have two limits, f of x and g of x, we add it or subtract. It can be added together or subtract. We call it the sum or the subtracting rule. Then when these two limits multiply each other, we can separate the two, which is the product rule. When the limit has a power, then we can call it a power rule. When the limit has nth root, then we refer that to root rule. We can have two limits whereby one is dividing the other, and in this case the denominator must not be 0. We call it the ratio rule. Then we can have three limits. In this case, each of them can have the same limit. We call it the sandwich rule. Then if we have limit c of f of x, then we can take the constant out. Then if we have limit of a constant, therefore the answer is also a constant. Although we have been familiar with this notice for the infinity, that infinity to the power of p is infinity, the infinity plus or minus a is infinity, infinity multiplied by a is infinity, a over infinity is 0, infinity over a is infinity, infinity divided by infinity is indeterminate. Now this is also applicable to some part of 0. Now 0 to the power of p is 0, 0 plus or minus a is a, 0 multiplied by a is 0, a over 0 is infinity, 0 over a is 0, then 0 divided by 0 is indeterminate. We need this for the examples we are going to solve. There are kinds of limits. The first is sided limits, where we have one-sided and two-sided. For the one-sided, we have the right side, the positive, and the left side, the negative. For the right side, the x0 has a positive, and for the left side, the x0 has a negative, because we are doing it on the left side, and for the right, we are finding the limit on the right side. Now, when the right and the left are the same, we have the two-sided limit. Now, where do we get, or where do we use the sided limit? Is whenever we are evaluating limits containing absolute values, such as absolute value of x, absolute value of x minus 2, absolute value of x to the power of 3. Then the next one we have is the infinite limit. The function f of x increases without bound. And in this case, the limit does not exist. We use dne. And we have in this form, that means the limit is infinity. When we graph this, we are going to have a vertical asymptote. Then the next one is the limit at infinity. In this case, x increases without bound. And when we have take the limit, we get L. The limit exists. When we graph this, we are going to have horizontal asymptote. There are few warnings. In the computation of limit, avoid getting an indeterminate form, such as 0 over 0. It is perfectly correct to obtain limit of f of x to be 0, but wary of getting limit to be infinity. It is often incorrect to say the limit of a function does not exist, that means dne, because you get the limit to be plus or minus infinity. The notation only gives information about the way in which the limit fails to exist. From the kinds of limit we have the limit at infinity. That also has several parts. We have the polynomial or the constant, we have the trigonometry, then the next one we have the rational, and the last one we have the exponential. The examples we can see now, we're going to solve that in the next section. Limit at infinity for polynomial or constant. We can solve this example. We want to evaluate lim x tends to infinity, x cubed plus 2x minus 5. Now let's pick the limit itself, then we'll plug in the infinity into it. In that case, we are going to have infinity to the power of 3 plus 2 multiplied by the infinity minus 3. Then we are going to have infinity minus 3 because infinity to the power of 3 is infinity, and then 2 multiplied by infinity is infinity. So when we have these two infinity together, we are still going to get infinity minus 3. Then the final answer is infinity because any number you take away from infinity will still remain infinity. Now, limit at infinity for trigonometry. Let us consider this example. We want to evaluate x tends to infinity sine 3x over 6x. But there is a rule that says that limit x tends to infinity sine x over x will give 0. We are going to apply this rule here. Now, what we have to do is that the denominator, which is the 6x, we can factorize that into 2 so that the numerator and the denominator will have the same number. So here we have sine 3x over 3x multiplied by 1 over 2. Now, we know that sine x over x will give you 0 if we find the limit as x tends to infinity. Therefore, sine 3x over 3x as x tends to infinity will give us 0 too. Therefore, it becomes 0 multiplied by 1 over 2, and the resulting value is 0. Limits at infinity for exponential. Let's consider this example. You want to evaluate x tends to infinity exponential minus 3x. We can write that as 1 over exponential 3x because the negative there in the index form can be written as this. Now the next for us is to plug in the infinity into the function, and if we do so, we have 1 over exponential 3 multiplied by infinity. 3 multiplied by infinity will definitely give me infinity, so I have 1 over e to the power of infinity. Then e to the power of infinity will also give me infinity, so I have 1 over infinity. In this case, 1 over infinity, which also means any number over infinity, definitely I'm going to get 0. Limits at infinity for rational as condition. The first condition is if degree of the numerator is less than the denominator, then the limit of the function is 0. For instance, we're given this limit. We need to check the power of the numerator, which is 2. Now we can see that this 2 is less than the power of the denominator, which is 3. Therefore, the resulting value of this limit is 0. Then the second condition, if degree of the numerator is the same as the denominator, then the limit is constant. What we mean by the constant is that the ratio of the leading coefficient. Then we also consider this example. If we look at the the power of the numerator, we have 5 in this case. Now, we see that the 5 of the numerator is the same as the power of the denominator, which is 5. Therefore, the value we're going to get is minus 2 over 7, which is the leading coefficient. The third one, if degree of the numerator is greater than the denominator, then the limit will be infinity. And we have given this example. Now, the power of the numerator is 4, which is far greater than the power of the denominator, which is 2. Therefore, the value we're going to get is infinity. Let's consider this example for limit at infinity. This limit, we can get the solution without working it out because we can consider the power of the numerator, which is 3, and that 3 is less than the power of the denominator, which is 5. So 3 is less than 5. The resulting value will be 0 based on the condition of the limit at infinity. But let's work it out. And for us to work that, we divide every term by the highest power of x. If we divide every term by the highest power of x, we are going to write it in this form. And once we do that, there are some values or power that are able to cancel out. Then we are going to arrive at this. Now, when we get here, we can then plug in our infinity. And when we do so, we are going to arrive at this. Then we can evaluate this. We are going to get 0 plus 0 plus 0 over 1 plus 0 plus 0. In this case, it becomes 0 over 1. And when we divide 0 by any number, we are going to get 0, which corresponds to the condition of the limit at infinity. For doing this, there are several approaches to evaluate the limit of a function. The first is the direct substitution, which is also called the plug-in. We have the factoring, we have the common denominator, we have the expansion, then the rationalize by conjugate. Then the last one, we have the absolute value. Consider the first one, which is the direct substitution or the plug-in. The direct substitution or the plug-in will fail if we obtain 0 over 0, definitely. Now, consider this example. We want to evaluate x tends to 1, x power of 2 minus 3, everything power of 10. In this case, what we're going to do is just to plug in our 1 into it. So we have 1 squared minus 3, everything power of 10. Then we're going to get minus 2 power of 10 when we do the subtraction. And when we take the power of this, we are going to get 1024. Let's consider another example that we want to evaluate this. Then the next thing we need to do is to plug in our value of 2. Then we have 2 to the power of 3 minus 3 multiplied by 2 plus 6 over minus 2 power of 2 plus 15. In this case, when we do it properly, we are going to get 8 minus 6 plus 6 over minus 4 plus 15. And when we do our addition properly, we are going to get 8 over 11. Another method is the factoring method. And factoring method can often work whenever plug-in method fails. Let's consider an example. We want to evaluate limit x tends to 1, x squared minus 1 over x minus 1. In this case, we see that if we use plug-in, we are going to get 0 over 0. So it fails. Now, the next thing we need to do is to factor the numerator. If we factor the numerator, we are going to have x minus 1, then x plus 1 over x minus 1. In this case, some cancellation can occur. Then, if we cancel out, we are going to be left with x plus 1. So we have limit x tends to 1 for x plus 1. And if we plug in the 1 there, we have 1 plus 1, which is 2. Let's consider another example. So we want to evaluate this. The same thing, if we try to do the plug-in, we are going to get 0 over 0. So the next thing is for us to factorize x squared minus x. So we can do it in this form to have x into bracket x minus 1 over x. Then the x can cancel out the x. We'll be left with the limit x tends to 0, x minus 1. Then we just plug in our 0 into that. We have 0 minus 1. And our final result will be negative 1. The next method is the common denominator. And for the common denominator, this method is more applicable if there is a fraction within a fraction in the given function. Let's consider this example. Mere looking at the example, we will then need to ask ourselves, is plug-in suitable? We see that the plug-in is not suitable because we are going to get 0 over 0. The next is that, is the factoring method suitable? We see that we cannot factorize, therefore factoring method is not suitable. So the next thing we need to do now is to find the common denominator. And for us to find the common denominator, we are going to express it in this form. So it becomes x minus 4 over 4x over x minus 4. Then the next is that we can rewrite this as x minus 4 over 4x multiplied by 1 over x minus 4 with the limit x tends to 4. Then we can cancel out minus 4 and then minus x minus 4 and the x minus 4, the second one. Now we'll be left with limit x tends to 4, 1 over 4x. Then we can then plug in our 4. We are going to get 1 over 16. Next, we have the expansion method. The expansion method is used by opening up the parentheses and then simplify. We have this example, but before we proceed, we need to ask ourselves some questions. The first is that the plug-in method will not work because we are going to get 0 over 0. Then the next thing is that the factoring method will not work because there is no way we can factorize that. Then the next is no common denominator in what we have here. So we need to just proceed using the expansion. Now we're going to expand x plus 2 power of 2. If we do that, we are going to have x squared plus 4x plus 4 minus 4 over x. So the plus 4 and the minus 4 will cancel out. We'll be left with limit x tends to 0, x squared plus 4x over x. Now we can then factorize in this case. And if we factorize, we have x into bracket x plus 4 over x. The x numerator and the x denominator can cancel out. After that, we'll be left with limit x tends to 0, x plus 4. Then from here, we plug in our 0 into it. We have 0 plus 4, and finally, we arrive at 4. The next method, we need to rationalize by conjugate. That means the function has a square root, therefore we multiply by its conjugate. Let's consider this example. Then we need to ask ourselves the normal question. Can plug-in work out? No, because we're going to get 0 over 0. The next, can the factorization work out? No, because there is no factoring number there. Then the next one is for us to ask if there is a common denominator, but there's no common denominator. Then the next is can we use expansion? There's no way we can expand anything from there. Therefore, we need to use our normal rationalize by conjugate. Now, we multiply the numerator and the denominator by the conjugate. Then we expand that. If we expand, we're going to get this. In this, minus 2 root x squared plus 4 can cancel out a positive 1. We'll be left with this. Then if we look at this, we see that 4 minus 4 can definitely turn to 0. Then we'll be left with s squared as the numerator and the s squared in the denominator with the square root of s squared plus 4 plus 2. Then in that case, s squared can cancel out s squared. We'll be left with 1 over square root of s squared plus 4, then plus 2. Now, we can then do our substitution. We can input the value of 0 into this. Then we'll be left with the square root of 4, which is going to give you 2, then plus 2. Then we have 1 as our numerator. In this case, we are going to get 1 over 4 as our final answer. Absolute value. The function has an absolute value, and the absolute value, the piecewise is given in this form, where we have x if x is greater or equal to 0, and minus x if x is less than 0. Now let's consider this example. We want to evaluate the limit x tends to 2, the absolute value of x minus 2 over x minus 2. We need to consider whether the plugin will work in, but it will not, because we are going to get 0 over 0. Then let's also consider the next one. Can we factorize? There's no factor there, so it cannot work out. Then the next is there a common denominator? But there's no common denominator here. And the next is, can we expand? Well, we cannot expand. And the last one is, can we rationalize? We cannot rationalize this. So for us to do this, we need to write this limit in form of the piecewise of absolute value. Now we are going to rewrite this to be x minus 2. The absolute value of x minus 2 will be x minus 2 for x greater than or equals to 2, then minus into bracket x minus 2 for x is less than 2. Now we are going to do the right hand side first and the left hand side and compare our results. For the right hand side, we are going to have x tends to 2 plus, then we take the x minus 2 divided by the denominator x minus 2. In this case, the x minus 2 can cancel out and we are going to get a positive 1. Now let's consider the next one, which is the left side. For the left side, we are going to consider the same thing, but in this case it will now be x tends to 2 with the power of minus, then the numerator will be minus, based on what we have there, minus into bracket x minus 2 over x minus 2. Then in that case, the x minus 2 can cancel out the x minus 2 at the denominator and the numerator. Now we'll be left with minus 1. And for that, the right hand side is not the same as the left side, in that case, it means that 1 is not equals minus 1. Therefore, the limit does not exist. L'Hopital rule, the powerful rule in limit. This method is commonly deployed for limits of functions with indeterminate forms by computing the derivatives followed by substitution. Now, the rule often converts an indeterminate form to an expression that can be easily evaluated by substitution. These are the indeterminate form we have: 0 over 0, infinity over infinity, 0 multiplied by infinity, infinity minus infinity, 0 to the power of 0, 1 to the power of infinity, infinity to the power of 0. The L'Hopital rule was named after a French mathematician, Guillaume L'Hopital. The rule did not originate with L'Hopital. It was first introduced to him by a Swiss mathematician, Joan Bernoulli. Now let's apply the L'Hopital rule to this. The reason for this is that if we use plug-in, we get 0 over 0, which is not applicable. Then if we try the factoring, it is also not applicable. If we look at the next one, whether there is a common denominator, but there is no common denominator. Then the next is we need to consider the expansion, but we cannot expand this. And then can we rationalize it, which is not possible. And the last is there any absolute value there? No. So we use the L'Hopital rule. And for us to use the L'Hopital rule, what we're going to do is we differentiate the numerator and the denominator. If we differentiate the numerator, we are going to get e to the power of x, while the denominator we are going to get 2x plus 1. Now we can then plug in our value x to be 0 there. So we put 0 in it, we get e to the power of 0, then 2 multiplied by 0 plus 1 as the denominator. Now e to the power of 0 is 1, then 2 multiplied by 0 is 0 plus 1. So we have 1 over 1. Our resulting value will be 1. We have few exercises here, so you compute the limits of the following. What you will do now is please pause the video and try the questions before proceeding. Now, the values for each question or the answers are these. If you like this video, please click on the like and subscribe button for more videos. And don't forget to drop your comment. Thank you.